Hello everyone, welcome to the next lecture in our blockchains architecture design and use cases course. We've gone through a good bit of background material on what blockchains are, some permission blockchain systems, Hyperledger Fabric, Hyperledger Composer and so on. We've also looked at a lot of use cases in a number of industries. I think it's now time to look at some advanced material, right? So these are all advanced material that are at the cutting edge of research and innovation today. So I'm glad you've all stuck on with this course until so long. So let's look at some of this material, and all these might also be a good starting point for you for maybe some of your projects, your theses even. So I'm hoping this is helpful for you. So specifically over the next 4 lectures, we're going to take a deep dive into security and privacy aspects of blockchain systems. This first lecture is just going to give you an overview of security and privacy, of some of the requirements of enterprise applications, what enterprise applications have on blockchain platforms. So let's just look at an open network. So this is like the Bitcoin kind of network, a permissionless network, where there is a certain notion of transactions where the transactions are all just exchange of bitcoins from one person to another. There is certain transaction validation, which is in the Bitcoin case, it is just prevention of double spending, making sure it's an authorized entity who is trying to spend bitcoins that they actually own. The security is really in the fact that you want to make sure the transactions are all valid before they are committed onto the ledger. And once it's committed onto the ledger, you want immutability. You want to ensure that no single participant is able to unilaterally modify the contents of the ledger. They can't manipulate other entities to also convince them to manipulate the ledger. So there are certain guarantees that are provided. So in the Bitcoin case, a certain fraction of the nodes, as long as they are not compromised, you can still provide this immutability guarantee. The privacy on the other hand, the only kind of privacy that they provide is through the notion of pseudo-anonymity. In some cases, although there are permissionless networks that have full anonymity. So we will talk about that later as in one of the lectures. And what are some of the assumptions? The assumptions to provide some of these guarantees in terms of security and privacy are that not more than 50% of the computing nodes have been compromised, right? So they're all, at least 50% of the nodes are following the protocol as stipulated. So they're not compromised, they're not malicious, and they're all functioning as expected. It also assumes that the user wallet with the private keys of the individuals are all safely maintained, they're not compromised either. And the fact whatever transactions you're running on blockchain, they also have to be deterministic. So Bitcoin and Ethereum achieve this by reducing the set of operations you can perform, but there are other ways to achieve this as well, right? These sort of assumptions may not always hold true, and there have been many attacks that have been shown on some of these open networks. So for instance, one of the most common cases is where either the user wallets or the decentralized exchanges have been compromised in some way, and users' secret keys have been stolen and bitcoins have been stolen because of that. I'm using bitcoins generically here, but there are other cryptocurrencies that have also faced a similar kind of issues. The ledger immutability can be compromised if nodes behave in a certain different way. So for instance, there is a research article that shows that even if you compromise just maybe even 25% of the network, you can actually you can cause bad things to happen in the network, right? So that's the notion of selfish mining. I will give you a reference to that later in the fun reading section. The other kinds of attacks, for the ones that support smart contracts, people try and exploit vulnerabilities in the smart contracts, what one might think as bugs in the smart contract, and that will allow the hacker to arbitrarily change the ownership of the coins maintained by the smart contract itself. Right? So these are all exploiting vulnerabilities in the application code or the smart contract code, not really in the platform itself. The platform might be secure, but the way you've written your smart contract is not secure. And one of the problems that platforms such as Ethereum have is that Ethereum purports that code is law, right? There is no governing body, there is no legal recourse if something goes wrong in your code. So there have been situations where hackers have hacked into the system, stolen coins, and because there's no legal framework to actually prove that this is theft and actually do anything about it, what ended up happening was there were hard forks and people actually had to undo transactions on the blockchain. So that actually goes against the principle of blockchain itself. It's supposed to be immutable and not subject to people modifying it by themselves. But it has happened that people have performed hard forks on the Ethereum blockchain, for instance. Okay, so in the enterprise world, apart from the fact that we have a shared replicated ledger, we want consensus, we don't want any one party having central authority, we want the ability for smart contracts to execute business logic, and we want all of this protected through cryptographic protocols. So apart from these properties, there are certain other properties that are not provided in a permissionless setting. For instance, permissionless networks do not give you strong identity management. It does not give you accountability, non-repudiation. It doesn't give you the ability to audit transactions. So I should be able to know, an auditor should be able to come in and find out who exactly did what. And more importantly, there is no notion of privacy. So we will have one dedicated lecture speaking of different notions of privacy and how there are different capabilities that are there in the security literature that provide some of these privacy guarantees. And privacy is also possible through design. Hyperledger Fabric has some of those concepts. R3's Corda, we'll talk about Corda in a few lectures. R3's Corda also has some of these privacy aspects. So we'll talk about what those are. And across all of these, we want to make sure that the performance does not degrade while we are providing some of these capabilities. Right? So let's go over some of these security considerations. We talked about strong identity management. This is to say that we want to ensure that only a permissioned set of entities gain access to the network itself. Others don't even know that this network exists or cannot read what's on the network. So the participation into the network is authorized and governed. So that's the strong identity management. And this is typical of enterprise systems because any enterprise knows that it's only going to do business with a certain set of other enterprises, and it at least knows of those enterprises. You're not going to be doing business completely with unknown entities, most likely. Although you know those entities, it does not mean that you trust them, right? So those are two distinct things. Then there is privacy and access control. So for whatever information, whatever transactions you are performing on blockchain, you want to make sure that only certain authorized entities are able to obtain access to that information, and they are also only certain set of entities are allowed to perform certain transactions, certain types of transactions on the blockchain, right? Then there is authorized execution. So this is to say that only certain set of entities should be allowed to see what the business logic is, see what the smart contracts are. It may not be that all parties in the network see all the smart contracts that are part of it. There might be different subsets of entities who need to know certain pieces of logic, and they are the ones executing that logic. And the next one is around accountability and non-repudiation. So once information is there in the system, we should be able to prove clearly that this information was in fact produced by this person. And then once with that proof, whoever performed that transaction should not be able to deny that they actually performed that transaction. And one person should not be, the corollary of this is also say one person should not be able to forge another transaction to make it seem as though it came from somebody else rather than themselves. Right? So that's the accountability and non-repudiation aspect. And we want all of these properties together with support for auditability. So we should be able to have regulators or auditors come in and see everything in the network, or whatever selective portions you want to reveal to them. We want this to be pluggable components. So in Hyperledger Fabric, almost every component is designed as a pluggable component. So the ledger is pluggable. So you can have different aspects of the ledger. We have CouchDB and LevelDB, and then you can have consensus as a pluggable concept. Just like that, we want all the security concepts to also be pluggable. Like the identity management should be pluggable, the crypto protocols should be pluggable, and we'll see how that is achieved in Hyperledger Fabric. And the reason is also that some of these security protocols also mature with time, right? So over a period of few years, these protocols keep changing and the best practices keep changing. And we want Fabric to be able to adapt to some of those changes and improvements in security literature. And like I said, we want all of these security properties with minimal impact to scalability, performance, consistency, right? So we don't want to compromise too much on the scalability and performance. Scalability is in the number of participants, how much the network can grow in size. Performance is in this throughput, right? How many transactions you can handle per second, or how quickly can you commit transactions, like what is the latency. So those would be performance metrics. We don't want to affect them while providing much richer security and privacy guarantees. So security and privacy is a key differentiation for Fabric compared to many other platforms that are out there. And Fabric, right from the beginning, has been designed keeping security and privacy as the foremost goal. And that's also some of the things we are seeing from clients, right? Security and privacy are the biggest things that clients ask of us when we are building Fabric or when we are building applications on top of Fabric. So there are many controls that are provided in Fabric to give you different notions of security and privacy. There is membership and access control. So at every stage of Fabric, you can have access control. So you can say who are the ones who are participating in a channel, within a channel who is executing chain code, within the chain code what are the endorsement policies, right? Who needs to sign off on a particular transaction. So that's really the endorsement policy. You can apply application level encryption to provide privacy guarantees on who gets to see the data. So unless you have the application layer key, the secret key that was used to encrypt the transaction, you won't be able to decrypt it. So then there are notions of channels. There is SiteDB. So we'll in one of the lectures, actually in this week itself, one of the lectures we'll talk specifically about SiteDB as a construct for providing data privacy. So we'll talk about that. And there are also hardware capabilities like trusted chain code execution using inside secure containers. Right? And apart from these, there are new concepts that are also coming in. So at the time of the recording, there is a new capability using Identity Mixer for providing anonymous and unlinkable transactions. So we'll cover that as well. It's going to be part of Fabric very soon, but it's not yet there. It's still in development. It's an open source. You can see the development in progress, but it's still not merged with the master branch of Fabric. So this is just a pictorial view of how at every stage there is some level of security and privacy embedded in it in terms of membership access control, endorsement policies, the notion of channels, SiteDB, and so on. And as I mentioned there, so there's also, apart from the protocol or the platform itself giving you security properties, we can also obtain security properties through cloud services or through hardware. Right? In IBM Cloud, the IBM blockchain platform, all the components of your network actually run inside secure services, inside what is called a secure services container. So this secure services container is an isolated container in pretty much everything, right? In terms of memory, CPU, in terms of disk, everything is isolated, and there are some additional properties. We'll talk about them. So your peer, orderer, chain code, all of them execute in separate containers. They're all isolated with each other from one another, and that prevents any kind of tampering that one organization might try and impose on another. Okay, so what does the secure services container do? So it's actually a combination of hardware and software. It has a firmware bootloader that's first loaded into memory. And once you have that loaded into memory, it then loads a software bootloader from disk. And when it loads this software bootloader from disk, it can actually do an integrity check. This is to make sure that what you read from disk was what was originally put inside. So you can make sure the disk has not been tampered with. And you can actually do that integrity check, and you can decrypt the software bootloader. So this is actually stored encrypted on disk. And the software bootloader, it actually has keys stored in. There are keys stored in the software bootloader that will enable you to activate encrypted disks. And this encryption decryption is done in flight when accessing appliance code and data that's residing on the disks. Right, so that's a kind of security that's all built into hardware and software as part of this secure services container. And the application is designed so that it can interact with the container only through APIs. So there is no concept of being able to SSH into the machine. There is no admin user. Even IBM will not be able to get into this container and look at what is inside. So when you develop an application, when you run a network, all of that is completely isolated, and even IBM will not know what's running inside. So you have complete control over that container that is provisioned for you. Right? The only thing IBM can probably do is shut down your container, right? But it's not in IBM's interest or any cloud provider's interest to actually do that. So the guarantee that is provided here is that even we will not have the keys, and we will not have the ability to get into your container and look at the data or the code that is running inside. The Intel Software Guard extensions, SGX, is an incredible innovation that Intel has come out with. It actually has similar features to the secure services container, but it's a bit different. So what it has is, within your application, you can actually have an enclave, and this enclave is usually a small piece of code that is trusted, and it's been verified, and it's known to be correct and bug free and all of that. And you can ensure that this enclave is protected from other processes that might be running on the same machine. Like for instance, this picture here in the bottom, you have an application here. You want to protect a portion of that application or the whole application itself from other malicious applications that might be running on the same operating system. So in the cloud, when you're using virtual machines, it's possible that multiple applications are running on the same operating system or the same infrastructure. So you want to prevent other malicious applications to be able to attack and obtain information from my application that I want to keep secure. So they have this notion of an enclave, and this is in hardware. It's a silicon chip plus a CPU microcode, and there is code that is running inside that enclave. And the code is basically isolated user level code, and that's protected from other processes that are simultaneously running on that system even at higher privilege levels. Then apart from that, you can, on the enclave code itself, you can do remote attestation. So what that means is, you can have a remote authority, centralized authority, verifying whether this code, when it comes up, has not been tampered with. So it's actually running the original piece of code that was running there. So that's the attestation aspect, and this actually provides like a reverse sandbox. So there's, within an application, there's a sandbox for you to protect certain piece of code or data in that enclave. And there are certain limitations to this, but I won't go into that. But this has caused a good amount of innovation in this space, the Intel SGX capability, and today, almost a lot of our laptops that are coming out today, they're all come with SGX capability. So if you dig into your laptop, you'll see that it's most likely has SGX in them. Yeah, of course, if you have an Intel chip on your laptop. So this next one is about now switching gears. A different framework is a framework that's come out. Microsoft has come out with, called the Coco Framework. I'm again going to talk about this very briefly because this is an overview lecture. So what this framework allows you to do is allows you to create blockchain networks based on different blockchain protocols, right? So for instance, you can have multiple consensus algorithms that you can plug in to your blockchain network. So this picture actually helps. This is actually from the Coco Framework white paper itself. So if you think about it, so what they allow you to do is they give you a pluggable way of plugging in your favorite blockchain platform, whatever that is. You can plug that into Coco Framework. You can plug in your own consensus algorithm into that framework for that platform, and it also has the persistent store, right? So it maintains the ledger for you. So there is a blockchain core. This is the pluggable component. You'll have to write an adapter for your favorite blockchain application. You can plug that into Coco Framework, and it will manage the consensus and the transaction execution and so on. And apart from that, it gives you permissioned identity management, and it also uses trusted execution environments. So each of these things, so if you see this whole thing is running inside an enclave. It's a trusted execution environment. This is actually, they're doing this with Intel SGX. And they also provide you capabilities for network management. Once you have this set up, you can do network management through a voting policy. So this is more like governance that Fabric provides, but a version of that for just providing how you can vote on your network management. So for instance, you can vote on whether a new organization should join your network or not. So it gives you an interesting set of capabilities basically for management and governance of your blockchain network, agnostic of the kind of blockchain platform that you want to use. So you can just have an adapter and bring in any kind of blockchain platform to it. So that brings us to the end of the lecture. So a bunch of fun reading for you to go through. So this, the first one is a research paper titled "Majority is not enough, Bitcoin mining is vulnerable." So this is the selfish mining that I talked about. So it shows how maybe even at about 25% network capacity, if you're able to take over maybe 25% of the network, you can actually do very bad things in the network. So that's this paper. It's a very interesting read. I would encourage you to read it. It's one of the hot papers that's been cited a lot of times already. And there is a survey on security and privacy issues in Bitcoin. So this is right now as a preprint available on archive, so you can go read that. I think it gives you a good overview of what would be some good properties in security and privacy and how Bitcoin does not have some of those properties. And Ethereum has had a few attacks on it. So this is the DAO attack. So it's a decentralized application organization. So there's a blog on that. So it gives you a good overview of what that attack was really about. This was really not an attack on Ethereum. It was an attack on a smart contract, which was the DAO. DAO is really a smart contract on Ethereum. So an attack on that and how they were able to steal certain Ethereum coins from that, right, Ether from those accounts. And eventually Ethereum had to do a hard fork to undo that hack, right? So some details about Intel SGX. So Intel itself has published, like, it's not a very long one, it's a few pages long, it's a HTML. You can go read that. It gives you a good overview of some of the nice properties that Intel SGX provides in terms of isolation and privacy. And finally, the Coco Framework white paper itself is again a good read. It gives you some of the properties that Coco Framework gives you. I'm sure this is for Coco Framework. If you read it, you'll see it's really work in progress. I'm sure Microsoft has more things in store that they're planning to bring out along with this. So with that, that ends this lecture. Over the next few lectures, we'll go at length at some of the security and privacy properties we need for enterprise applications. And we'll look at some examples of how that is provided by Hyperledger Fabric. With that, thanks a lot. We'll see you at the next lecture.